Okay, so last time we used group theory. To show that name, which is the name of your crush, is cute. And we did that by first defining a set of symbols. S, and then we define an operation on S, which is plus, which is a binary operator that takes two inputs or two symbols from S and gives us another symbol in S. And so name and cute are symbols, right? From the free group over our language we established in the very first lecture, and they were both inside S, and then we created a quotient group out of S mod some symbol Pn, which is just, you know, S sub Pn. We also showed that it is isomorphic to Z mod N, or just mod N. And so from there we made another definition that states that if they are in the same congruence relation, or if because name is inside the congruence relation of cute, we surmise through that one definition that name is cute, or name is equal to cute, and, you know, by that definition. And that definition was just basically us abusing notation and saying that to if an object, or if a symbol in S is inside the equivalence class of another symbol, then we say that those are, instead of congruent, we just say that those are equal. Because here there are no other notions of equal, not in the case of, because here we're talking about modulo, not really this binary operator. We're not defining our, you know, addition or our equivalence via this addition, but rather under our modulo thing. And yeah, so we use group theory to show that name is cute. So for today's lecture, I'm actually a bit thankful that I reviewed the paper, because I realized something that was very wrong in my constructions. So I will get to that later. Okay. So we're gonna need to discuss a little bit, or today's lecture is gonna be a bit abstract, but I will try to provide as much intuition as possible. So in this lecture, we will be using measure theory. So for today, we will be using measure theory to show that your crush is cute. So unlike last time, wherein we defined your crush as a name, or we abstract them as a name or as a symbol, today we're going to be using the same symbol, but the same symbol will represent not a sort of collection of not an object or mathematical object, but we will be sort of representing it as a map, right? As a map from one measure space to another measure space, or the same measure space, or yeah. So okay, so we will be using measure. I said that a while ago. We will be using measure theory. And to start with that, we need to define what exactly a measure space is. And a measure space. So first, and most important definition is a sigma algebra. So what is a sigma algebra? The sigma algebra is a very simple concept. So I have a set X. So I'm going to use S because, you know, let's make it a set of symbols, S. A set S of symbols. So, okay, let S be a set. Let S be a set. Next, let mathcal P of S be its power set. So according to the axioms of ZFC, there exists a much larger set of S, which contains all possible subsets that we can make from S. So if S contains the symbols A, B, and C, then the power set of S is equal to this set. So first, the set A, B, C. The empty set is part, because every set contains nothing as well. A, the set A, the set B, the set C, the set AB, the set BC, the set AC. And it doesn't matter the order of these subsets, but this is the power set. So every single possible subset we can construct from the elements of S is its power set. Okay, and that's just an example. And I'll set that aside so you guys can sort of contemplate on that. Okay. Okay, so if I have power set of S, we will need that later. Right? All right. So let's get to it. A subset. So a subset of the power set of S. We're taking some collection of subsets from S. A subset. I'll call it mathcal M inside mathcal P of S. Power set of S is called a sigma algebra of S if and only if it satisfies the following conditions. Let's be a definition. So it's a definition. So the first condition, we only have 3 conditions we need to satisfy. Unlike the topology, which requires so many or some conditions, the sigma algebra only requires 3 conditions in order, or a certain subset of the power set of S is called a sigma algebra only because of 3 conditions. The first condition is that the empty set and the set S itself are elements of this subset M. I have to make that broader so it doesn't look like mu, because mu will come in handy later when we actually define what exactly a measure is. Okay, the second one is that M is closed under complement. So M closed under complement. Okay, so what I mean by it is closed under complement is that, okay, I have my set S. So this is S. So we sometimes think of these sets as blobs, alright? Especially topology. Okay. So I have a set S and I have M. Let's say this certain subset here is M. Okay. So what I mean by closed under complement is that if I have a small little section of M, I'll call it A. Okay. The complement of S of A with respect to S, so everything that's not inside A but is inside S is contained inside M. Okay. So yeah. So S without A is inside M. Or at least it's a subset of M. So you'll notice that here in this example, M is already not a sigma algebra, because when we take the complement of A with respect to S, we notice that there are some elements that are not inside M. So the entire complement of S must be inside M. So given this example here, this ABC, so I'll erase the visual example and focus on the more symbol-based example. Okay, so I have this over here, this ABC. So the set ABC here can technically be a sigma algebra, because if I take B away, right? If I take B away, or if I take the singleton set B, right, and remove it from S, the remaining stuff in here are still inside the sigma algebra, which is ABC. Okay. So if I let my sigma algebra or my supposed sigma algebra or alleged sigma algebra be the set A, B, C, it is a sigma algebra. It's a sigma algebra because 3 dots represents because I don't want to have to write because the entire thing, because I'm going to take a subset B. So M, take away the element B, is still inside M. Okay. So ABC is in fact a sigma algebra, or one example of a sigma algebra, because of this second one here, or at least it satisfies this second one. Okay, so actually this is not a full-on sigma algebra because it doesn't have the entire set inside it. Actually, yeah, but it fails the first condition that the empty set is inside it, so we have to put here the empty set. So empty set is part. Okay. So that's SpongeBob. And in fact, I will show you guys later, or I will tell you guys later that in fact, there's something that the power set is actually known for, or really great for, when it comes to this topic. Okay. So the third condition is that M is closed under finite union or countable union. Under finite union. And what I mean by that is that if I have a bunch of subsets, or if I have an index amount, or if I have an index sequence of sets, A sub I have an index sequence of sets A sub I, wherein I is inside some index set J, then it holds, or if all of these are contained inside M, okay, all contained inside M, it must hold that their union for all I in J of A sub I is also inside M. Okay? So another reason why this over here, this M here for this example, is the sigma algebra is because, okay, I'm going to take the subsets A, B, C, and the empty set, okay? Now, if I take their union, right, okay, I'm going to show why this over here is a sigma algebra. Okay, the first one, it satisfies the first one, it contains the entire set. A, B, C is the entire set already, and it contains the empty set. It's inside here, alright? So S is inside M, and so is the empty set. Alright, it looks like semi. Okay, so second one, it's still close under complement, because if I take away, say, B, okay, I'll just point it out here to this example here. I take away B, the complement is still inside M, okay? It's still inside M. And the third one, the third condition, it's close under finite union. So I'll take the union of the singleton A, the singleton B, and the singleton C, and the empty set, okay? Which are a sequence of subsets that are inside M. And that's just equal to A, B, C, and then the empty set. Which is precisely here, or it can be contained inside here. We can say that this is a subset of that, and then, you know, it's technically there already. Okay? So this practically just degenerates into the entire set here, because you can just write this this empty set as nothing. You know, it's technically not part of there, but it's still there. It's implied to be there all the time. Okay? So it degenerates into the entire set, and we have shown that the entire set is part of the sigma algebra. Okay? So therefore, this M here, this example M for this example S, you know, set containing ABC, is a sigma algebra. Okay? So to sum it up, a sigma algebra is a bunch of stuff, or a bunch of subsets of S, or part of the power set of S, such that 1, the empty set and the set is inside that set. 2, M is closed under complement, so if I take away a subset from the sigma algebra, the remaining elements that are inside the sigma algebra, or the remaining elements inside our set, is inside the sigma algebra. And third, it is closed under finite union. So if I have a bunch of subsets inside my sigma algebra, my alleged sigma algebra, then it must hold that their union is inside or a subset of the sigma algebra. Okay, so this is where I define what exactly a measurable space is. There's a difference between measure space and a measurable space. So, now the definition, I just take my original set S and equip it with its sigma algebra, gives a measurable space. Okay. So I just take my original set and equip it with its sigma algebra, and that gives me a measurable space. Or what is called a measurable space. Alright. Alright. So I'm not going to define anything further aside from the fact of a measure. So next one. Next definition. Now this is the reason why I want to write M like this. Like it's full on, because it may look like mu. Okay. A measure, so we're now coming to what you guys intuitively know to be something like volume, length, mass, something like that. All of those are measures, okay? Or examples or special cases of a measure. A measure, okay, a measure, okay, first we say it's a map. A map, mu, that maps our sigma algebra M onto our union set plus and union set minus infinity. This is also called the affinely extended reals, because usually the real numbers don't contain minus infinity and positive infinity, partly because maybe the algebra breaks down. But for the case of measure theory, we will include them as their own elements. So we include new elements or new symbols called plus infinity and minus infinity inside R, and that gives me the affinely extended real numbers, which we denote by R with a dash on top. Okay? And the reason why partly we want to do this is because when we do take limits and stuff like that, as you recall in calculus, we can legitimately make the claim that if at some point a function becomes unbounded, then we can make a legitimate claim that at that point the limit of that function is precise, or the limit of the function as x approaches that point is precisely positive infinity. Or if it becomes unbounded in the negative direction, then it's minus infinity. So there. So this map will map our sigma algebra or subsets of our sigma algebra onto this affinely extended reals. So this map is called a measure. And another reason why we need to include these two is because we will have certain measures, right, that gives us infinite measures, such as, say, the counting measure, okay, which basically asks us to count the elements of a set. And you all know that the set of, or the counting measure of the naturals or even integers is infinity, all right? And that's what we need this thing. Okay. So it's called a measure. And of course, this definition will come important later, and why exactly we need to use the affinely extended reals. Okay, let's go to measure. If and only if, one, for all subsets E inside the sigma algebra, the measure of each E is greater than or equal to 0. Okay. In other words, if I have a subset of my sigma algebra, or an element in my sigma algebra, its measure is positive, always positive, or 0. The case wherein it's 0 is when it's a singleton set, when it's a set that only contains one element. Okay? Now the next one is that 2, the measure of the empty set is 0. Of course, naturally speaking, because this empty set contains nothing, right? Let's say, for example, that we want to consider the counting measure. Again, how many elements are inside the empty set? 0. No elements at all. Or let's say if you want to envision the empty set as a shape, if you can even like do that, you'll notice that what is the volume of the shape? Nothing. There's nothing inside the shape. What even is the length of the shape? There is nothing. I mean, if you think of it as a line, what's the length of the empty set? The empty set doesn't even have a length, so it's 0. Its measure should always be 0. Okay. So third one, for all countable collections of pairwise disjoint sets in my sigma algebra, it must hold that the measure of their union is equal to a sum of the individual measures. So I take a bunch of elements E1, for any E1 En inside my sigma algebra, it must hold that the measure of their union equals 1 to n of E sub I is the same as the sum running from I is equal to 1 to n of the individual measures of E sub I. Okay? And this condition is called sigma additivity, and it will come very important. It will be very important later because we will get into a very rigorous proof on why exactly subsets of the reals and maybe by extension the affinely extended reals is Lebesgue measurable. Okay, when we get to Lebesgue measure, because the Lebesgue measure will be a very important premise of today's lecture. Okay, so that's all. Okay, this is all a measure has to satisfy. So the first one is that for any subset that we're mapping or that we're taking or putting into the function from our sigma algebra, it gives us a positive value. The second one is that the measure of the empty set is always 0 because it's practically nothing. What should be its measure? Nothing. It should be 0. And last one is that for any sequence or for any disjoint, what I mean by disjoint is that they have no intersection. They're not intersecting. Okay? I mean that in the literal sense, like think of two blobs, any blob you want to. If they don't like cross each other and stuff like that, if you observe that there are no elements inside each of them or both of them, then those two are disjoint. That's what I mean by disjoint. So for these disjoint subsets of the sigma algebra, it must hold that if I combine them together, right? If I combine them into one singular set, the measure of that set is the same as if I did the measure of each individual or each subset, right? I did the measure of each subset and then I add them together. So we can think of it like this. I have a line, right? I have a line, let's say I have 0 to 1. And I want to measure their length, right? So that's one thing, or one measure, the length of a line. So I know that all throughout, the length of this line is just 1, right? It runs from 0 to 1. Okay, so what I mean by this third property is that that property of it being of length 1 must be the same as if I split it in half and say, okay, I'm going to split it at 1/2, alright? So the interval 0 to 1/2 not included, and then this is 1/2 and up to 1. So these two, if I combine them together, if I combine these two intervals together or make a measure from them and then add their measures, it must sum up to 1. So you notice that the measure of this interval, or this small mini line of this gigantic line, is precisely 1/2. And the measure of this is also 1/2. And you know that 1/2 plus 1/2 gives us 1, which is the original measure that we want. So the length measure is, or the length map, you could say, is a measure because it satisfies this third condition over here. And of course, it satisfies the second condition because, you know, what's the length of nothing? 0, right? And so, and also, of course, it's always positive. There's no such thing as a negative length, right? I mean, of course, you could think of negative numbers as maybe debt in finance or economics, but when it comes to distances, or I mean, if you think of velocity, maybe it's moving backwards, right? But in reality, especially in measure theory, when we measure distances, it's always positive. There's no such thing as negative distance, because that just sort of breaks common sense. I mean, I know we're supposed to throw common sense out the window, but maybe employ a little bit in saying it's crazy to think that there could possibly be a negative length. So yeah, the length of a map is a measure. So that's why we call it a length measure, or that's why we call length a measure. So it's a mathematical reverse of calling length a measure. Length measure, not measure. Okay, so, alright, so if I return to my original measurable space here and equip it with this map mu, which is a measure, we get something called a measure space. Okay. So what is an example of a measure space? Well, there is something called, or we could work with R. So you guys will notice that R, of course, equipped with its sigma algebra. I'll call it just sigma, and then I have my distance function. This over here is a measurables, or a measure space, okay? Because you notice that, okay, what's the distance of the empty set with itself? Nothing, 0, alright? So the second one, that's the second condition, alright? So the distance of any 2 points, okay, so distance of xy is simply, this is r1, so it's just a length, okay? It's not like, you know, a line that joins 2 points on a plane, okay? So that's just x minus y. And the reason why we put the absolute value is to make sure, right? And this is how we defined it back then, the absolute value of x minus y, right? So this will never be negative, okay? I know this may sound a bit circular, but this is really how we defined it before. Even in elementary, we defined it like that. And intuitively, this works, this definition works, right? And it satisfies the first condition for a measure. Okay, so next, all right, so the third condition is a bit tricky on how to prove that this is a measure on that. Because, what if I have multiple points, right? So, what I have to do is just nest the function into itself. So, I have 2 sets of points now. So, so I have an x and then a y1, and then an x, or so I have 2 distances maybe, x2 and y2. So I have 4 points, x1, y1, x2, and y2. Don't think of these as coordinates now, but think of these like as a nested sort of thing. So I find the distance between x1, y1, and I find the distance between x2 and y2. So it gives me the distance between x1 minus y1 and x2 minus y2. And that gives me the absolute value of x1 is y1 minus absolute value of x2 minus y2. And assuming that these two become or stay positive, right? That gives us x1 minus x2 minus y1 minus y2. And these will stay positive so long as after we perform the absolute value, it's positive. And it will always be positive when we take absolute value. So there, it satisfies the third condition. So this distance is a measure. And in fact, this over here would be what we call a topology. It could be a topology, after all. It's a collection of subsets. So this is an example of a measure space, actually. Okay. And I think the reason why you may not consider the affinely extended reals to be a measure space is because when we do try to find the distance between infinity and itself, that would imply a subtraction of infinity with itself, which is not defined. Which could be anything. It could be 0, it could still be infinity. So yeah, that's why it's called undefined. Alright, So notice the difference between a measurable space and a measure space. A measure space is a measurable space with a measure, okay? But a measurable space is just a set with its sigma algebra. Okay. Alright, so now that I have defined a set and its sigma algebra, let's dive into the Lebesgue measure. Okay, so what exactly is the Lebesgue measure? Or not Lebesgue, but Lebesgue measure. Okay. I think it was made by, or it was named after Henry Lebesgue, which is an Italian, I think, or a German mathematician, which started integration theory. All right. Okay, so the Lebesgue measure is a translation invariant measure. What I mean by that is that if I shift the interval which we're measuring, or the subset we're measuring in R, then the measure won't change unless I scale it or unless I add something into the set. In fact, I don't think it would even affect the measure if I remove an element from the set, but we won't focus on that for this lecture. Okay, so this mostly works, or we mostly study Lebesgue measure in Rn, okay, or in spaces that are isomorphic to Rn, okay. And recall again from the last lecture, isomorphic basically means they have a bijection and the operation carries on over. So far in our conquest of studying measure theory in order to make this course, to make this theory work, so far we have not encountered a use of the Lebesgue measure outside Rn. So be comfortable in the fact that we won't be using complicated space such as Cn or RPN, or maybe the space of the Mobius band or something like that. Okay. So yeah, we'll work in Rn, which is basically just the real axis, the n-dimensional real axis. Okay. So let's begin with a subset of Rn. Or actually, yeah. So the Lebesgue measure of this, which we call lambda, or which we denote by lambda, is a collection or a union or a sum of measures, right? Okay, we can think of this, the Lebesgue measure on X, as a collection of cubes, right? Of cubes that cover X. So let's say that X exists in R2. So the Lebesgue measure is a collection of let's wait for my bird to calm down. Yeah, usually one of them is when they start making noise. Alright, so I can cover it with a bunch of squares. So, okay, I'm just gonna let you guys fill in the details. So, okay, so the Lebesgue measure is basically all of those squares I can cover the shape with. So, think of it like a generalization of an integral. So, originally, we don't know how to find the measure of this space. We don't know what the heck is the volume or the surface area of this shape here, or the area itself. Okay, primarily we don't. So what we do, we find out using the shape we know the area of, because you know the area of a square is just the length squared, right? Yeah, the length squared is just basically the area of it. So what we do is cover the shape with these squares, which we know the volume or the surface area of, and then sum those surface areas to give us at least an approximate of the measure of this set. Or if it's an interval, we cover it with a bunch of mini intervals that can overlap. So these squares can overlap, right, to give us a good measure. So I can fill this up with a bunch of intervals such that the sum of all those intervals should cover. What I mean by cover is that it basically, literally covers the entire shape. So here, it literally covers the entire interval, even though it might go beyond the bounds. Okay. Now, the precise definition of a Lebesgue measure requires us to define something called the Lebesgue outer measure. So, the Lebesgue outer measure. So, actually, the Lebesgue measure is also called as n volume. Now, for the one-dimensional case, it would be length. For the two-dimensional case, which is a flat shape, give us an area. Three-dimensional shape, volume, four volume, or however you should call it. So it's called n volume sometimes, or it's also known as n volume. And it is like I said, it's a generalization of length, of surface area, of area itself, and volume. All right. So let's first define what exactly the Lebesgue outer measure is. So to do this, let's start first with the base case. Let's just start with the real axis, just one gigantic line that extends off into infinity, which contains all the real numbers you can think of. So start with an interval I, which can be closed or open. A, B. That's in X, not X, but R. R1. So start with this interval in R1, or it's just a line, basically. Okay? And let L of this interval, L of I, equals B minus A, be the length of the interval. Okay? This is the length of the interval. So it's length of I. Okay. Next, I want to consider another interval. I'll call it E inside R1. Okay. So another open or closed set in R1, which is another length. Okay. Okay. So the Lebesgue outer measure of E. So really, we're not considering this I over here, but we're considering this E here when it comes to the Lebesgue outer measure. So the Lebesgue outer measure of E, which we denote by lambda, but with a star, of E, is this. It's the infimum. It's the infimum of all sums run from k equals 1 to infinity of the lengths of an index set of intervals k, such that I sub k, k in the naturals, is open or closed in R1, with E being inside their union. Okay. So what I mean by this is I have a bunch of lengths. I have a bunch of lines ik, and I take their length, or I have a bunch of intervals ik, and then I take their length, right? And then I sum up all those mini lengths. So this is what I was talking about a while ago, about boxes and overlapping lines. So originally, these guys will overlap, or may overlap, alright? And what's important is that they are open in R, and that they cover the set we want to take the measure of E. Okay, so what I mean here, this symbol over here means that E is inside the union of all of these. So if I gather them all together into one gigantic line, E is inside there, or E is a part of that line, or at least it becomes E. Alright? So it covers E. And the problem with this is that, again, as I said, they will overlap. So what do? We want to take the infimum of all of it. We want to minimize the entire thing. So what we want to do is shrink the sum. We want to shrink the sum, or find the smallest possible sum that isn't 0, right? the smallest possible, this entire thing, or entire sum, or length, or interval, such that, the overlapping stops, like, so the error starts reducing, and it becomes or converges into precisely E, okay? So originally, you have a bunch of overlapping sets, and then E is inside here, and then this is IK. So when we minimize all of these guys, they suddenly start getting smaller and smaller, and then they eventually become E. So that's what we mean by taking the infimum of this entire thing. Alright? So now that we have defined the Lebesgue outer measure, okay, so now we have the base case, which is just R1, but now let's generalize it to a higher dimensional space. For R2, what we do is instead have a box, a bunch of squares or rectangles that we fit into our shape or into our subset of R2, and sort of just take the union of all of them, or the infimum of their sums, or infimum of the sums of their infimum of the sums of their area, basically. Alright, so now if E is inside R2, right, this time we consider a bunch of indexed cubes IK cross IK that cover E, and then the area of this IK cross IK. Okay, so that's the area of IK, which is IK or IK times IK, or the length of IK times the length of IK. Give me that square. Okay, so the Lebesgue outer measure now of E is equal to the infimum of the sums, infinite sums, so n equals 1 of the areas of these IKs cross IKs, such that the condition a while ago, that they are open in R2 and that they cover E. So the union of all of these boxes cover E, or E is inside their cover, or their union. So there, the Lebesgue outer measure for R2. Now for R3, consider a volume, so the space enclosed by the shape now, or enclosed by a cube, and just stack them all together and stuff like that. So it would look something like this. And then just expand that three-dimensional model or visualization. So in general, if I have an E inside Rn now, so n, any natural number, the Lebesgue outer measure of E is equal to the infimum of the sum running from k equals 1 infinity of the volume, the n volume of some ck, such that the stipulations a while ago. So the union of all those ck's covers E and are open inside Rn, and ck is defined to be hypercube. Okay, so ck. No, C, just C, regular C. And this is an indexed amount of them. So, yeah. So, it's a product of open intervals. So, I have an I1 cross the dot cross IN, and then the volume, vol of C, gives me the lengths, or the products of the lengths. IN. And then all the stuff that follows from there. Now, lastly, we want to state that there are some subsets E of Rn that satisfy something called the Carathéodory criterion. mean by that is that if I have another subset A inside Rn, it must hold. So for any A in Rn, the Lebesgue outer measure, or the Lebesgue outer measure of A, okay, is equal to the Lebesgue outer measure of A intersect E plus the Lebesgue outer measure of A intersect the complement of E. So whatever is not inside E. Alright? So this condition. Excuse me. I'm suffering a cold right now, so do excuse me if I keep sniffing or sneezing or something like that. Excuse me. Okay. So in that case, the actual Lebesgue measure of E, if this holds for E, it holds that the Lebesgue outer measure of E is precisely the Lebesgue measure of E. Okay? So all that implies. Now, I'm gonna show you guys an important result which we will be using in our thing. And no, actually I think I could just discuss this in a footnote. So I'll just state it here. So we're close to the meat of the actual lecture. So this is the actual thing I want you guys to know. Okay, so let R inside math BBR and okay be an n-dimensional rectangle. Be an n-dimensional rectangle. Okay. Okay. Then it holds that they satisfy the Carathéodory criterion. Or R satisfies the Carathéodory criterion, the CC. And another thing to note is that when a set of Rn satisfies the Carathéodory criterion, we call them Lebesgue measurable. Or R is Lebesgue measurable. Now, not all subsets of Rn is Lebesgue measurable. An example, this is a Vitali set and a piano, not a piano set, but a Cantor set. These both are not Lebesgue measurable, but their constructions are a bit complicated, and I will reserve that for a different lecture. Okay. So this is all you guys need to know for now. In a footnote, I will prove this result. Okay? Alright, so now we have that. Let's jump into the actual thing that you guys will be interested in here. Okay, so we have two definitions here. So definition 1, let X, which is a subset of Rn, be an abstraction of your affection with or of your crush. The Lebesgue measure of n, define the Lebesgue measure of n, or X, to be the precise measure of affection, denoted by A, mathematical A, 2 F's, and then you set X. Okay? So first we abstract your affection as a singular set in Rn, and then the Lebesgue measure should surely be the precise measure of your affection. So if you have a high amount of affection for this person, then your set should be a big interval, and then its length or its volume or n volume should be the precise measure of that affection for that person, for your crush, of course. Now, the second definition. Okay, and this one's going to be the very important one, to be honest. Okay, a surjection or a map, which I will call big psi, that maps R or N onto the tuples, N tuples of the affinely extended reals. Okay, so this would be an n-dimensional analog or n-dimensional analog of the affinely extended reals. So this is n-dimensional affinely extended real numbers. Okay, so the two are the same dimension. Okay, so a surjection that's like that, such that. So it's non-trivial over any, of course, number or any subset of Rn. So it's not the same as that. Is cubed. When the affection, okay, measure or the affection of the image of X under that map is at infinity. And this is precisely why we needed the affinely extended reals. Because what we're saying here is that a sudden change in your affection for anything or anyone, or for one person, right, is cute when the affection becomes infinite. When your affection for that certain person becomes infinite, like it reaches beyond anything, or it's the largest possible element in your thing or in your set or in R. So yeah, that's why we need the affinely extended real numbers. To be precise, af of the psi of X is positive infinity. Of course, you don't want minus, or you don't want a negative amount of infinite affection. What kind of relationship is that? Toxic one? Psh, that's right. We're not talking about toxic affections here. We're not talking about toxic relationships here. Only good vibes is gonna happen in this channel. Thank you, sir. All right. Okay. So now let's consider one particular map. All right. So I hope you guys already took note of these definitions. So here's the actual theorem. It will be wildly. I want you guys to note that this theorem will be wildly different from our original theorem. From the theorem in the paper, I mean. It's going to be wildly different. The map R to R extended. So we're only considering a length right now, okay? Just intervals, not the general. Defined to be, so the image is I'm going to define this pointwise, okay? So it's X plus infinity, X equals the infimum, or the supremum of X. So the last element in X, X plus 1. So I'm going to shift it for any X that's sandwiched between the infimum and the supremum. Okay. So for any X between the infimum and the supremum. X could be equal to the infimum here. Okay. Alright, so that's it. So I'm going to rewrite that so it's clearer. So it's X plus 1. I'm going to generalize it to another parameter that's positive. I'll call it epsilon. For x that's less than the supremum of x. And epsilon, of course, is a positive real number. Not finally extended, because I don't want you guys to think that it is, positive infinity, which will screw things up in our map. Okay, so there's our map. And it's still a surjection because each of these guys are sent to a different element or some other element, but there are probably some elements that are not mapped one-to-one here, such as those that are at infinity. Okay. So yeah. So what we're basically saying here is I'm gonna extend the end of the interval or the line up to infinity, make it infinity, basically. Because any number added to infinity gives us infinity. Okay? And so what we mean here is that this is just the supremum of x, or that b, or in a up to b. Okay? Okay. Wait. It's not sine. I'm gonna have to extend this a bit. So name defined to be. Theorem. The map, which is name, the name of your brush, which is defined to be big psi. Okay? Is Q. So this is Q. Okay, so we're gonna prove this theorem via induction. Okay. So let's start with the proof. Start with the base case. Start with the base case. So I'll let x be equal to the unit interval 0 to 1, which is 0 to 1. So the psi, big psi of 0 gives 0 plus epsilon, which is just epsilon. Alright? And the psi of 1 is precisely 1 plus infinity, which is infinity. Alright? Okay. So here our affection is 0 to 1, and so its precise affection is 1, unitary. But that doesn't mean that your affection is low for this person. Okay, it could still be considered 1. Alright. So psi, big psi of x, gives us the set, which is epsilon, and then the element after 0. Okay, so it's dot dot dot, because this is an uncountable set, then positive infinity, which we can denote to be epsilon running to infinity. For any epsilon that's positive and real, okay, but not affinely real. Okay, so it's that. Now, and so I'm gonna have to draw a line over there. And so the af of this psi of x gives us plus infinity minus epsilon, which is just positive infinity. So there, we proved that the base case here, put through this map here, gives us positive infinity. So infinite affection, which shows that this map is Q, or which name is Q, under the base case. So now let's do the inductive step. Okay. Next, I'm gonna let 0 and 1 now be 2 letters. So let x be the closed interval a plus 1 and b plus 1. Okay? So you want to show that we still get infinity from doing this. Okay, so big psi of a plus 1 is equal to a plus 1 plus epsilon, right? and the psi of b plus 1 gives us b plus 1 plus positive infinity, which is equal to b plus infinity, which is just infinity. Alright? And for any in between these two, the same thing applies here. They get shifted by epsilon. Alright? So, lastly, so the psi of big X gives us the set a plus 1 plus 1 plus epsilon dot dot dot, and that is plus infinity close brace, which is defined to be the interval a plus 1 plus epsilon dot 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 plus infinity. And we can show that this here is simply, if we replace a plus 1 with 0, right? It's just 0 plus epsilon, which checks out with our base case. Right? And it's the same, it happens to become the same if we replace a plus 1 with any arbitrary number, which you could say is x, I guess. It could be x. So therefore, yeah. So the affection of psi of this x is equal to plus infinity minus a plus 1 plus e. And according to our rules of adding and subtracting with infinity, all of this just becomes plus infinity, which ends the proof. So this is our measure theoretic way of saying your crush is cute. So yeah, because of these conditions and this inductive step, name is cute. So there. So yeah, I think I'm just gonna add the timestamp to the most important part, which you guys want to hear. So yeah. So this will be it for this lecture. In the next lecture, we will be moving on to a short detour into calculus. I believe it will be very short only. We will be considering, or maybe you could call it real analysis. We will be considering the space of all functions, real valued functions over R, and then do the same kind of definitions wherein a certain shift in the functions would give is classified as cute, right? And then define that as name. So that will be the next lecture, and this is a good place to stop.